So today I would like to tell you about negative probabilities, about my recent research on this topic together with Stochastic. And also I would like to advertise some very, very recent results with Doug and also with Guo Buchau. So this will be at the end of my talk. All right, so first, just a few words maybe about motivation, why negative probabilities. Because I think that still many people consider negative probability as Andrei Krenikov by Sekeli and also many other people studying this. But to me, my motivation to study non-locality is this beautiful result that was, as far as I know, shown independently but in these two papers, showing that, first of all, if you have non-signaling, you immediately have a joint probability distributions. And in addition, if you want to be non-signaling plus non-local or contextual in general, then this joint probability distribution needs to go negative. So this is a very beautiful picture that actually captures main properties of quantum theory, namely non-signaling and non-locality or contextuality in general. And in addition, there is one thing that I find particularly interesting, and I think this may be an interesting avenue of research, namely, we know that quantum computation works. There are plenty of algorithms, quantum algorithms that are better than classical algorithms. But people may say that they work because of entanglement, because of superposition and many things. But in the end, I believe that still we do not fully know why quantum computer works. And this is actually the problem why it's so hard to find new quantum algorithms. So I think that it might be very interesting to say, okay, let's start with classical computation theory and add a little bit of negativity into it and see what can happen, whether we can get some speed up, so some super computation. And then if it works, maybe we can translate it back to quantum computation and maybe this would be a new way to find quantum algorithms. And of course, people may say that, okay, everything may sound nice, but we have a problem because how to interpret these negative probabilities. And of course, I'm not attempting to give an answer to this question, but what I would like to say is that we have the same problem in quantum theory. We have probability amplitudes, and we also have problems with interpreting them. So quantum theory is like input-output theory. We have classically understandable input, then something happens in the middle, and then we have this classical output. So it's like I think Gell-Mann was calling quantum theory this great smoky dragon. Like we see the head, we see the tail, and there is something strange in the middle. All right, so let me go straight to the idea. So the idea is the following. I want to concentrate all negativity on a single smallest possible system, namely two-level system, which I'm going to call Nebit. So it's a system that has two different states, let's call them 0 and 1. And the probability of 0 is inflated, so it's larger than 1. It's 1 plus delta. Probability of 1 is negative, it's minus delta. So you see this delta somehow measures the amount of negativity and will appear throughout my presentation. Okay, and now the point is the following. What happens if we take standard classical probability theory and evolution of this probability, so general like stochastic processes, and we supplement them only with the single Nebit? What kind of things can we obtain? What kind of strange phenomena that diverge from classical phenomena? So in general, what kind of non-classical phenomena can we obtain? And in particular, can we simulate that way some aspects of quantum theory? And if yes, then how big negativity is needed? So these questions were asked in this paper that was just recently published. So if you're interested, please go there. All right. So what are the rules of the game? As I said, quantum theory is input-output theory. So in the similar way, I would like to play here. Namely, we assume that our input is some D-level system. So we have some D events, and we have a standard classical probability distribution over these D events. So everything is greater than 0. The same thing must happen at the output. So we have at the output, we have joint probability distribution over D events, and it's a proper non-negative probability distribution. But in the middle, we supplement our system with the Nebit. So suddenly this state of this set of events is multiplied by 2, because each event gets this additional substructure. You can have a Nebit in state 0 and a Nebit in state 1. Okay, and now you can have something strange going on, but what's important after all the computation and tracing out of this Nebits, to just like calculating a marginal probability distribution, summing over this outcomes of this Nebit, we should obtain a proper distribution. So what's happening inside? So how this probability is going to evolve? So I'm assuming it's going to be a standard Markov chain. So we have some probability vector at time t describing our events. And then the probability at time t+1 is simply given by a multiplication of this vector by a stochastic matrix, so namely a matrix whose entries can be interpreted as probabilities, and the sums of entries in the column sum up to 1. So it's a standard stochastic process theory. But now imagine that some entries of this matrix will go negative. So in this case, we will speak of quasi-stochastic transformations, and this is where interesting things will start to happen. And of course, what's important inside this quasi-stochastic matrix, despite the fact that some entries are negative, columns still add up to 1. All right, so you may ask right now how to implement a quasi-stochastic matrix. And it's a quasi-stochastic transformation, and it's relatively easy. Namely, you take your classical system described by this probability distribution and you supplement it with Nebit. And now you perform a global stochastic operation on both systems. And then after this operation, you just forget about this Nebit. So you're only interested in this marginal probability distribution over your system. And in fact, what happens on your system is, after tracing out this Nebit, is basically this quasi-stochastic operation. So basically, this Nebit uses this negativity to implement this operation, and then in the end you have this probability distributions which might be negative, but again, this is not the end of the whole process. We are still inside the box. So here we allow the system to be negative. All right. Now every stochastic process can be actually interpreted as a random walk, where events are vertices of some graphs, and stochastic matrix implements transition between vertices of this graph. So for example, Sji corresponds to probability of transition from this node to this. Sij is a probability of transitions here. But right now, imagine that we add this Nebit, and of course we cannot look at this Nebit. So what happens? It's like every vertex, every event here right now has this internal structure, because the Nebit can be in state 0, just like here, and the Nebit can be in state 1, just like here. Okay, so this internal events right now will be denoted by this double vertices, and the hollow ones will correspond to the Nebit value 0, and the full ones will correspond to the Nebit value 1. And right now you see that actually we can have a much richer structure of much richer evolution, because we can have also some evolution inside this hidden structure. So there can be a transition between this full vertices and hollow vertices, and so on. Actually, we can also have transitions in the middle, which I did not represent in this picture, but of course it's possible. What is important, and this is a very crucial constraint on the dynamics, is that of course we allow some of these events, this internal events, to be to have negative probabilities or inflated probabilities. But what's important is that the probability of being at some vertex must be a standard classical probability. So basically, for all I, the sum over pi0 and pi1 must be greater or equal than 0, must be a proper probability. And right now, let me show you just a few examples of what can happen once you allow for such a thing. So let me start with the following example. Imagine that we have a chain of positions and a particle that can jump from one position to another. So let's say we have n positions, and right now we add a Nebit. So basically, what is represented in these pictures? 1 means that particle is in vertex 1. Here, 1 dash, and 1 means that particle is in vertex 1, and Nebit is in state 0. 1 dash means that particle is at vertex 1 and Nebit is in state 1. Okay, 2 in a similar way. 2 means that particle is set at vertex 2 and Nebit is in state 0, and 2 dash means that the particle is at the same position 2, but the Nebit is in state 1, and so on. So basically, dash means that Nebit is in state 1, no dash means that Nebit is in state 0. So this is the internal structure, but what we see is basically the sum of this dash and without dash, the probabilities of the sum of the probabilities on these two vertices. And this is the dynamics. This dynamics is completely deterministic. So basically it tells you that the state 1 goes to state 1, the state 1 dash goes to state 2, state 2 dash goes to 3, and so on. 2 goes to 2. So everything I think is quite clear here. And now, so basically what's important, you see that this kind of dynamics allows the particle to jump only to either to stay at the same vertex or to jump to the nearest neighbor on the right. Okay, so imagine that at time 0, your probability distribution is the following. Of course, it's a negative probability distribution. So all these dashed vertices are assigned probability 1. Now, all these vertices without dash from 2 to n are assigned probability -1, and this probability and this vertex 1 without dash is assigned probability 0. Okay, so this is the following probability distribution, and it's quite clear that the sum of everything is equal to 1. And now you may ask, what's the probability that particle is at position 1? So you basically need to sum this probability with this probability, which is 1 plus 0, which is 1. But for any other vertex, the sum of these two corresponding probabilities is 1 minus 1, so it's 0. So we definitely know that at time 1 and time 0, the particle is at position 1. But right now, let's perform a single step of this dynamics here. So what happens? This probability is added to this probability, this is added to this, and so on. This probability stays the same, and this probability stays the same. So after one step, you see that this is the state of the system. I mean, this is the probability distribution. 0 is everywhere except 1 here, here at this position. So it means that probability that particles at position n is equal 1 plus 0, 1, and probability that particles elsewhere must be 0. So you see a very interesting non-local effect, namely the particle in one step jumps from position 1 to position n, despite the fact that dynamics allows the particle to move only one step to the right, at most one step to the right. And actually, such a thing may happen in pre- and post-selected quantum theory. But I mean, if you're interested, I can later tell you more about this. Okay, another thing, another example is search algorithm. I think that people interested in computation might be more interested. I mean, may like this example a little bit more. So basically, what's the idea of the search algorithm? So right now we have this graph. The vertices represent some elements of a database, and one vertex, one element of the database is marked, and this is what we want to find, but we do not know which one is marked. So basically, initially we start with a random distribution. So let's say that we have n vertices, so this initial random distribution is like that. We are randomly distributed over a whole graph. And then we can allow these probabilities to evolve. And of course, if we are at marked vertex, we want this probability to concentrate at this marked vertex. But we know that any classical algorithm based on classical random walk allows to solve the search algorithm in time, which is basically proportional to n, so linear in n. Now let's see what happens if we add negativity. So if we add Nebit, these vertices are doubled, just like I showed you a moment ago. And right now we introduce the following transition rule. So we added this Nebit, and right now, if the Nebit state is 0, then basically we allow these probabilities to jump from every vertex to any other vertex freely. So it's basically, if you are at a certain vertex, you just choose randomly any other vertex and you jump there. Now, if the Nebit is in state 0, then basically if you are in a vertex that it's not marked, you jump to any other randomly chosen vertex. But if you happen to be at the vertex that is marked, you basically stay there. So that's why you have this loop. So this is basically the transition rule of a standard classical search algorithm, with the only exception that here right now we have this additional hidden structure, and inside this hidden structure is this negative probability. So I'm not going into details. I'm just telling you what is the result. You can show that the time of the search depends on this amount of negativity. So as I said, if delta is equal to 0, so basically if you have a standard probabilistic algorithm, then this time scales as n, so linearly with n. If delta is like square root of n, then the time of search is also square root of n, so it's exactly the efficiency of the Grover algorithm. But if your time, if your delta equals to n, you can see that you can perform the search in one step. So in one step, you can find your marked vertex. So this clearly shows you that actually adding negativities, the single unit of negative probability to your classical system, evolving in a classical way, allows you for a computational speedup, even greater than in quantum case, if your negativity is large enough. All right, so now let me go to this result that I told you is very recent, so it's still in preparation. Is the problem of local activation of non-locality. So imagine the following scenario. It's a standard non-locality scenario, but of course it can be a contextuality scenario. But let's focus here on non-locality. So we have Alice, we have Bob, and imagine that they share classical correlations. So we know that if Alice and Bob share classical correlations, definitely they are not going to violate any value inequality. So in the sense, they are local. On the other hand, we also know, there were many papers on this topic, that if we allow this joint probability distribution between Alice and Bob to be negative, they will be, of course, non-signaling, but they can also see some non-locality. So they can violate some Bell inequality, okay? And now the question, can we go to this non-local distribution only by allowing Alice to add Nebit on her side? So basically, we only locally add negativity at Alice's side, not at Bob's side, only at Alice's side, and we activate non-locality between Alice and Bob. And this is doable, and actually this can be done in a relatively simple way. So let's start with standard CHSH scenario. So imagine that Alice has two different measurements, A1, A2. Bob has also two measurements, B1, B2, with binary outputs plus minus 1. And then imagine that everything is described by a joint probability distribution. So it's the joint probability distribution of outcome A1, A2, B1, B2. Again, A1, A2, B1, B2 are plus minus 1. So it's given in the following way. This expression here in this bracket is this well-known CHSH expression, and we know that if A1, A2, B1, B2 are plus minus 1, then this expression can be at post 2 or minus 2. So you immediately see that if alpha is less equal than 1, then this joint probability distribution is a proper non-negative joint probability distribution. Now, if alpha is greater than 1, then you become non-local. If alpha is less than square root of 2, your non-locality is achievable within quantum theory. So square root of 2 is this famous Tyrrellson bound, and when alpha is equal to square root of 2, the violation of the corresponding CHSH inequality will be 2 root 2. Now, of course, we can go with alpha higher. We can exceed quantum theory. So we can even reach PR box. If alpha is equal to 2, then the violation of our CHSH inequality, I mean, the value of the CHSH expression will be equal to 4. Now you may ask, what happens if alpha is greater than 2? Of course, we can go higher with alpha, but then we have a problem that the marginal probability distributions of, let's say, A1, B1 become negative. So we violate the rules of our game. So that's why alpha should be contained in this region between 0 and 2. So again, you see, right now, let's start with the following thing. Let's say that alpha is less equal than 1, or let's say that alpha is equal than 1. We have maximal classical correlations that saturate this bound of 2. Nothing negative, no violation, no non-locality. But right now, imagine that Alice applies to her system, to her 2 random variables, A1, A2, the following stochastic matrix, or it's actually a bistochastic matrix because both rows and columns sum up to 1. There is a single parameter, beta, and you already see that if beta is greater than 1, then this bistochastic matrix actually becomes quasi-bistochastic because we have negative entries, right? The amount of negativity inside your Nebit that's needed to implement this matrix is given by this. So you see that it's quasi-bistochastic if beta is greater than 1. So delta in your Nebit needs to be given by this, right? And then you see that this matrix has a very nice, application of this matrix on this probability distribution has a very nice scaling property. Namely, if you multiply this matrix by, on A1 and A2, on this joint probability distribution, you see that this joint probability distribution will have the same structure, only this coefficient alpha right now becomes alpha times beta. So if beta is greater than 1, you see that actually this coefficient increases. So we increase correlation, and if alpha is equal to 1, then already beta, which is like infinitesimally smaller, larger than 1, already creates some non-locality in your system. Okay, so if you right now ask how large beta to achieve quantum maximal quantum non-locality, here is the collection of results. So I'm here presenting you the results also not only for a CHSH scenario, but also for general multipartite scenario, like GHZ non-locality or non-locality, which is expressed basically by Mermin inequality. So, okay, if you have 2 parties, you have a CHSH inequality and beta, assuming that initially alpha was equal to 1, so maximal classical correlations, then if beta equals to square root of 2, you will achieve maximal quantum value. If you have 3 parties, Alice, Bob, and Charlie in this Mermin scenario, then it is enough if Alice uses a single Nebit that provides beta of 2 to achieve maximum non-locality between all 3 parties. For 4 parties, beta at Alice's site needs to be equal to 4 and so on. So in general, for n parties, beta needs scales like that. All right, so here are the conclusions, but I think that's already my, I don't have enough time, so I'll stop here. Thank you very much.
Thank you very much, Pawel. You are actually a bit ahead of time, so you haven't up your 25 minutes, but we have now more than 5 minutes for questions and comments. So please go ahead.
Can I ask a question here, Haneshti speaking?
Of course.
Thanks for the nice talk, Pawel. My question is, your Nebits are inspired by negativity in quantum theory. So I was wondering if you can simulate Nebits using quantum mechanics, even for a small delta in a natural way.
But could you be a bit more precise? Because what do you mean? I mean, of course, if you have a, let's say, 2 qubits, and you have a singlet state, so it's like, let me go to this presentation, and you have a singlet state, then you now know that amounts of negativity in this joint probability distribution that would violate the CHSH inequality would be corresponding to this beta equal to square root of 2, okay, or delta. I mean, if you put the beta square root of 2, you can basically evaluate this delta. But I mean, do I understand correctly that you would like to simulate it on a real, like, two-level system? Or?
Yeah, no, I was wondering if you can simulate Grover and the random walk results that you presented for Nebit using a quantum system, because quantum systems do allow the amount of negativity. I was wondering if there's a natural way of mapping a Nebit to quantum systems so that quantum mechanics can simulate Nebits. You see? Of course, I mean, you can always write a program that simulates it, right? Rather indirectly. But I was wondering if there's some more natural mapping.
Okay, I actually do not know what to tell you, because our main idea was basically to use Nebit to simulate quantum theory. And the whole idea of Nebit was basically to concentrate all this negativity on something, I mean, the smallest possible system. And now you would like to simulate the smallest. I mean, of course, standard Grover algorithm would allow you to go to the speed up of square root of n. But what of course with Nebits, as I show you, you can achieve even better results, which is not allowed in quantum theory. Although there were some results that if you have nonlinear quantum theory, you can even have a better performance, but still with nonlinear quantum theories, we have problems. So I think it's a different story.
Oh, okay. Fair enough. Thanks.
I'll be happy to discuss it, because I'm sorry, I'm not sure that I fully understand the
question. No problem. Thanks anyway.
Okay, so other questions, comments?
Can I ask a question?
Yes, by all means.
Yeah, so I was wondering, like for the Grover, you were showing that you're depending on the value of delta, you have different amount of speed up and all. So here you get, like, let's say if I put delta equal to root n, then I get the root n is like a speed up and all. And we know that the root n is the lower bound from the query complexity results and all. So I was wondering, like, based on this, can we say that how much delta is, let's say, allowed in according to consistent with quantum theory. So for example, if you have this when we're playing the bell games, there also I saw this root 2 number coming. So can we say that somehow this are they related to each other, the root 2, root n, are you putting some kind of using known ideas from quantum theory? Can we put some constraint on, this is the delta, that should be present, and you can maybe talk across different algorithms and all, and maybe use it to give some lower bound on algorithms and all.
I don't know, but I think it's a very good question, because in general we may ask how much negativity. I mean, we know that quantum theory is something that happens in the universe, yes, and now we know that it can be simulated with negativity, and then the question is how much negativity is allowed by fundamental rules of nature, yes. So it's along this line. So if we really have some cap on this, then indeed we would be able to put some upper bounds on efficiency of algorithms and so on. But
so for example, if you put delta equal to, I couldn't quite see the relation of the delta that you have here and in the bell game. So so let's say if I put delta equal to scaling as for n system scaling as root n, then will that recover the 2 root 2 bound? And maybe that could be thought of as some physical principle to recover quantum mechanics. I don't know.
That basically if your system is of the size n, only the root of the negativity of the root of n is allowed somehow. Yes.
Yeah. I mean, that's what this the Grover